And, whoa. How did that happen? Well, this was just supposed to be a review slide anyway, so that should have just made sense. That looks fine there. I guess I'll just accept that. Okay, so you should have this review slide handy whenever you go through and work through your problems. It was messed up, right? Okay, just making sure. Just so that you know what's going on, you've got it referenced so that you can look back at it and kind of make sure you're not missing something when going through and putting together structures. Okay? Try to condense a whole bunch of stuff onto one slide. You'll notice as the semester goes, I'll continue to build slides like this, okay, just to kind of review everything. I will also pretty much review over the important topics from previous lectures, so if you've got questions from a previous lecture, it may not be a bad idea to make reference to it when you see the slide. Much like hybridization. How's everybody doing with hybridization? Getting any better? Worse? Okay. In general, what we're looking at is just trying to understand where the electrons are, okay? And it explains some of the bonding patterns that you see within each of these structures, okay? So it's looking at explaining what orbitals or how our atomic orbitals change to reflect our molecular structure. Yeah?
For each of the p orbitals, do they go in to two? Do two of them go into one first, or do... Like if you had 3 electrons, would they make a pair with a negative and positive spin, or would one go into each of them?
That's going to be relevant to your atomic orbitals, which we don't need to worry about anymore, okay. But it's going to fill singly first.
Okay, so fill each one up.
Yeah. More on kind of simplifying with your VSEPR shapes, the valence shell electron pair repulsion theory. And hybridization. So one of the repercussions of hybridization is we end up classifying our bonds slightly differently than we've seen before. Okay, instead of saying single, double, and triple, we'll now classify them as sigma and pi. The more pi we have, the more double or triple bonds we've got. So every time you see a bond, okay, regardless of how many lines there are, one of them will be a sigma bond. Okay, that sigma bond is made up of a hybridized orbital, which is where we're getting that sp to begin with. Okay, so if we look at our sigma bonds, it's always going to involve some type of s orbital. Okay, be it an s orbital that's been hybridized with some p orbitals, or just a straight s orbital in the case of, say, hydrogen. Okay, when we move up to multiple bonds, double and triple bonds, those are going to involve the overlap or indirect overlap of unhybridized p orbitals, okay? And that's where we get our double and triple bonds. Okay, hybridization can be a bit tricky because you got to make sure that you're looking for the correct groups. Okay, so our electron groups are going to count as lone pairs and sigma bonds. So when we see a pi bond, for instance, if we looked at this functional group, how many electron groups are around that center carbon? We end up with 3 electron groups. In this case, all sigma bonds. You'll notice that we don't count the pi bond in that system. That's going to be explained by the unhybridized p orbital left over. Okay? How many electron groups are around the oxygen? Just to make it trickier. Greater than or less than 4, greater than 2. There are 3 electron groups around that oxygen. Where are those 3?
2 lone pair and 1 bond.
We absolutely have the sigma bond, which is where 1 is, but we also have to remember those irritating organic simplifications. If we have a neutral oxygen with 2 bonds, it must have 2 lone pairs. There's our other 2 electron groups. Okay? On tests, you can expect those to fall off if I'm asking for you to remember those simplifications. If I'm asking for something else, like the reactivity of the oxygen, you'll probably see the lone pairs on there. Okay? Whenever I draw them up, I will try to make sure those lone pairs show up so that we don't forget about them. Yeah.
What if it was positive, so you lost one?
So if we had a positive, let's just clean everything off. Actually, might as well stick with this. Okay, we'll leave off the lone pair for the moment. If you have a positive oxygen, how many groups of electrons are around that? There's still a lone pair. How many groups of electrons? 3. Okay? So watch out for that. This is why that organic simplifications, all the individual assumptions and implications that might show up during the semester. That's why I tried to summarize it on that slide so you can make sure you find them.
It's a little pragmatic because you technically have the double bond and then the single bond, so that would be...
Okay, so we've got sigma bond, we have sigma bond,
Yes.
and we have lone
Why
pair.
would the lone pair be there if you have a positive charge? Because it completes the octet?
It has to have its octet. Yep.
Okay.
So if we were going to go through and do the Lewis structure for that oxygen, we have 2, 4, 6, 8 electrons around
It
it.
has to have a positive charge.
That comes back to the balance of how many electrons it brought in. So if we calculate formal charge, how do we calculate formal charge?
Okay, so the positive just a formal charge.
You don't get away that easy. How do we calculate formal charge? 6 valence electrons minus number of bonds. How many bonds do we have? We will count all of those. 3 minus 2 gives us plus 1. There's our formal positive charge. Okay. The positive charge can be deceptive, okay, particularly when looking at reactivity. So we'll talk about that when that actually pops up. So just be aware the positive charge or your negative charges can be helpful for identifying chemistry, but they aren't the final end. Okay? More questions with this? Okay, some other simplifications that might show up in that. Erase. Okay. I've summarized the hybridization for each of those, the bond angles that you'll typically see, and then the main class of shapes. Okay. The secondary shapes are also shown up along those sides. If you want to look at those, or if you're asked questions about that from the textbook, feel free to answer them based on those. Okay? Questions? Yes?
I know we touched on it, but what was the energy levels? Which one's the highest and which
So, energy levels. So when we go through and try and evaluate these, it's not going to be particularly helpful to look at the sp3 hybrid orbitals. Okay? Because they're all equal. Okay? So we can't really see a difference in energy when we move to the sp3s. So let's ignore those for the moment, and let's take a look at, say, the sp2s. Okay? I did rank these according to their energies. You'll notice the sp2 hybrid orbitals are all at the same energy level, and the p orbital is higher in energy. Why should the p orbital be higher in energy than our hybrid orbitals? How did we make those hybrid orbitals? We combined our atomic orbitals. So we can go back and take a look at our atomic orbitals. The energy of our s orbital is kind of our 0 point in this graph. Our p orbitals are higher in energy. If we take an sp2 hybrid, we're going to end up with an energy somewhere in between. Okay? It should be lower than the p orbital because you're adding s orbital, which has a lower energy. Okay? So that explains why our p orbital is higher in energy than our sp2. If we were going to compare our p orbital back to the sp3, should our p orbital be higher or lower than our sp3s? Why should our p orbital be higher? Doesn't have any s orbital character. Okay? Whereas our sp3 still has that s energy, dropping the energy of that orbital a little bit. Okay? So if we were going to go through and rank our energy, go ahead and cross that out, say energy. That says energy. You can trust me on that. We can start with our p orbital, then we can move into our sp3, followed by our sp2. sp, what should be our lowest energy? S. Okay? That would be high and low. I guess I should have written P there, huh? Okay? Questions about that? Is that all you needed? Just a clarification on it? Other questions? Okay. Step 2 through here. Roots of functionality. So this is pretty much what we're going to spend a lot of today looking at, is starting to evaluate some reactivity, maybe look at some basic reactions. Almost all of them come back to functionality, come back to electronegativity. Okay, so it's helpful to have a rough idea of everything that's going on with your periodic table. You'll notice your electronegativity increases. I know this is angled, but your electronegativity increases from, what is that, left to right, and from top to bottom. Okay, so that can be good enough to be able to process and answer most questions. I did summarize some of the more common ones that you'll see here, so that can be helpful to evaluate. In general, I've classified them as either high or low. You'll notice that some of the high, particularly the ones in quotes, aren't particularly high, particularly in comparison, say, to the ones in the low category. Any ideas why I might have done that? What's that? No?
High compared to what they usually react with.
It's going to come back to their reactivity. Okay? I classified these in the high column as being high because those atoms will typically carry the partial negative charge within a structure. Okay? They're going to attract electron density to them. It's not always based on electronegativity. There's other things that contribute to our partial charges that show up. Okay? Electronegativity just happens to be the easiest and the most tabulated, so it's easy to make reference to. Okay? So if you see an atom or a bond between a low and a high element, the high is likely going to be partially negatively charged, and the low would be partially positively charged. Why would we start to generate those charges? Say if we picked carbon and oxygen. Why would the oxygen start to become partially negative? Okay, it comes back to its electronegativity. Electronegativity is the ability to attract bonding electrons. So if we take a look at the electrons in the bond, those electrons are spending most of their time on the oxygen, meaning the oxygen has gained electrons. What happens if something gains electrons? Becomes negative. What happens to the carbon? It's lost electrons. It's now going to become partially positive. Okay, if we think back to the quizzes, if we compared now carbon, nitrogen, what charge should the nitrogen become? Should be partially negative. Why should it be partially negative? It's one of our high electronegativities in comparison to carbon, which is our low. Which carbon is more positive? Red or blue? Okay, what's making it positive? The atom that's attached to it. That atom has to take electrons away. The ability to take electrons away is our electronegativity. So if that carbon is attached to a more electronegative element, what happens to its charge? It's going to become more positive. It's losing more electrons. The most positive carbon in this structure is our red one, because it's attached to the more electronegative atom. Okay? Questions about that?
Is there a way to calculate a numerical value on that partial charge?
No.
So we just...
And by no, probably, but
we just
not
use,
necessary.
We just use the relativity of them.
Yes.
Okay.
So one of the things that you'll find with organic chemistry is really nice because we typically don't deal with numbers. We're a lot more kind of qualitative as far as comparing things go. Okay? If we even look back to our electronegativities, I said high electronegativities for iodine and bromine, both of which are darn similar to carbon. Why did I say? Or why did I say that they were high? Because as far as their chemistry goes, their qualitative chemistry, they end up acting like they're high. Okay? So it's more looking at the results or the chemistry than looking at the specific numbers. Okay? We looked at intramolecular bonds. Okay? I've got an example up here just for clarification on the intra. Intra means within. So within an individual molecule, we will have bonds. Okay? We've got three bulk types of bonds: your ionic, your polar covalent, and your covalent. You'll notice if we go ahead and look at the polar covalent, anything bound to oxygen, nitrogen, or a halogen, what were the electronegativities for all of those? High or low? High. Okay, so it goes back to those electronegativity tables and understanding what's happening with those. If we're going to look for a reaction, which type of bond is going to be the most reactive? As a guess. I'm hearing ionic. Why ionic?
Seem pretty steady.
Because we have those plus and minus charges. Okay? Charges are inherently bad. You don't stick your finger in the electrical outlet because there's a lot of charge in there. Okay? So if we're going to try and classify these and figure out which one's the most reactive, we would expect ionic to react fairly readily as far as organic chemistry goes. Okay? Those also tend to be fairly rare. So while they might be the most reactive, how often are we going to see them? They're rare, so probably not very often. The class that we're going to be most concerned about for most of the semester is going to be your polar covalent bonds. Why do we not worry about the covalent? It's neutral. Okay? There's no reason for it to react with anything. Everything's striving for neutrality. If it's already neutral, we aren't going to be as stressed about it trying to react with something. There's no reason for it to react. Okay? Questions about the bonds? Okay. What bonds are in each of these? Sodium chloride is what type of bond? We get ionic. How do we know it's ionic? We've got a metal and a non-metal. Good call. Carbon, hydrogen. How do we know it's covalent? Our difference in electronegativity, or I like that answer. That's the definition we're working with. Okay? Oxygen and hydrogen, polar covalent. Oxygen and carbon, polar covalent. You'll notice that we're going to start to shift. We're no longer looking at intra, we're looking at inter. Inter is looking at multiple different molecules. Okay? So in this case, what I've got drawn up on the board here is we're looking at a water molecule with an intramolecular bond between the oxygen and the hydrogen. If I want to look at an intermolecular force, I'm going to have to look at a second molecule. How that second molecule interacts with my first one, that interaction is an intermolecular force. Okay? These are related, and we'll discuss that relationship in just a second here. Okay? So, let's start to look at some examples of our forces. Sodium chloride interacting with a second molecule. So we've got a nice example here. Which interaction is favored? Top or bottom?
Top, they form a crystalline structure.
Okay. Top is the answer. How do we know it's the top? Sodium versus chlorine. Okay, that's ionic, so we would expect ions to show up there. Where should our ions fall? What ions should we use and where should they be? What atom should they be attached to? Chlorine is negative because gains electrons. Why does it take electrons? Highly electronegative. It takes the electrons from what atom? Sodium. So what charge does sodium become? Okay? We can go through and do that on the other two versions of our molecule. And we said all chemistry is striving towards neutrality. So if I take my negative chloride, I want to try and neutralize that as best I can. How do I neutralize a negative charge? With a positive. So what do I want to put it closest to? The positive sodium. The top interaction is our favored one. Draw. There it goes. Okay? Let's come up with a name for this. We started with an ionic bond. Okay, in both cases. So we could call the force that connects those two what? It's intermolecular, true. Let's take it a step further. Let's give it a specific name. Okay, let's come back to that. Maybe we can come up with a name in a second. Let's take a look at the next case. Whoops. Sorry, jumped ahead. Yeah, we can go ahead and leave those. Which interaction now? Top or bottom? Who says top? Who says bottom? Okay, we get at least one adventurous hand. Why do you say the bottom?
Because CH is the definition of a covalent bond, so there's not as much charge, so it's not really attracting a charge, it's attracting a duet to be perfect with the height. I just kept talking.
It's a good idea. You brought up that it's a covalent bond. So what charge does a carbon build?
Well, it's
Neutral.
theory is neutral, but
The
they're
electrons don't shift between those. Covalent bond. By definition, we said that's our difference. There is no sharing of, or there's equal sharing of electrons, which means the charge on the carbon is neutral. What's the charge on the hydrogen? What's the charge on this carbon? Neutral. Which interaction is favored? Neither. Both are possibilities. Okay? We don't have a polarization that we had when we looked at the ionic bond. Okay, so this brings up why I was attempting to push you guys into naming our first interaction. Why do I want to name it? Because I've got different forces. There's something else going on here. If I've got a different interaction, I want a different name for it. Okay? So let's see if we can figure something else about this. Which of these do you think might be stronger? Our sodium chloride or our carbon hydrogen? Our sodium chloride. Why? Why would that be a stronger interaction? It's going to be related to it. I've got a negative charge. What does my negative charge want to do? It's going to want to attract the positive to neutralize. To do that, I want to have a very strong interaction between those two because I'm trying to neutralize. When we go down here and take a look at this hydrogen interacting with the carbon or even with that hydrogen, is there any charge to neutralize? No. It already started neutral. So why should it interact? There isn't a reason to do so. So what is that going to say about strength? We would expect a very weak interaction for those and a much stronger one for our ionic. Okay? So if we try and come up with names for these, okay, being the creative people that we are, for our strong one, we came up with strong force. I was just kidding. You'll typically hear it referred to as ionic. The other common one, in an attempt to make it less confusing, electrostatic. Why would it be confusing to refer to it as an ionic force? Because we have an ionic bond. They're referring to two different things. One's within the molecule, one is looking at different molecules interacting. Okay, and we give them the same name. Pretty silly. Okay, how about in our weak force? Well, this interaction was so weak that we decided to begin with that it's completely irrelevant. So if it's irrelevant, we don't name it. Then some famous guy came along and said, actually, it's not 100% irrelevant. What famous guy did that? Van der Waals, in the ideal gas law. Went back and said the ideal gas law didn't work. Why did it not work? Because of this force. That attractive force between gas molecules was one of the reasons why ideal gas law doesn't work outside of ideal situations. Okay? And because some guy found it, of course we could name it after him. You'll typically see Van der Waals or London dispersion forces. Or because, as you might have guessed and will continue to hear, I'm lazy. LDF. Okay? All molecules have London dispersion forces. Why do all molecules have London dispersion forces? What is that attractive force? This is why I like London dispersion as opposed to Van der Waals.
The electrons they're constantly moving.
Yep.
So there's constantly an imbalance.
So there's constantly, electrons around an individual atom are constantly shifting around, which means at any given instant, part of the molecule exposes the nucleus. What charge was your nucleus? Positive. Well, if all of your electrons shifted away from the nucleus, you've now got part of your molecule that's negative and part that is positive. You now have a very temporary and very weak ionic type interaction. The electrons can quickly shift back, okay, neutralizing that attractive force. So anything that has electrons has Van der Waals or London dispersion forces. Okay? What happens when we move over to the other two cases? And I'm going to pick oxygen-carbon. Which interaction is favored, top or bottom? What type of bond do we have between oxygen and carbon? We've got a polar covalent bond. Which atom is more electronegative? Oxygen, which means what does it do to the electrons in that carbon-oxygen bond? Pulls them towards itself, which means what charge does it build? Negative. We'll use the little delta symbol, okay, for our partial negative. What charge does the carbon build? We can go through and apply those partial positives and negatives to everything else. Which interaction is favored? We end up seeing the top one favored because same reason as our ionic, positive to negative. Okay? So it's that neutralization of charge that drives a lot of the interactions that we end up seeing. Okay? Is this one, or could this one be considered a London dispersion force? Not really. We're looking at partial charges. Okay? Could it be ionic? Not really. It's partial charges, not full charges. Okay? So we need to come up with a new name for this. Okay? Again, we get really creative with this. We've got a positive and a negative here. Okay, so we've got something similar that we might relate back to, say, physics. Okay, we have a north and a south end of a magnet. Okay, so if you take the south end of a magnet near the north end, what happens? They attract, right? Same thing that's happening here, positive to negative. Okay? That magnet has two ends to it. It's another name for an end. Pole. It's another name for two. Di. We put it together. The oxygen-carbon is a dipole because it has two poles. How about the other one? It still has two poles, so we can call it a dipole. Being creative and original, we have a dipole-dipole force. Okay? Those are our three primary intermolecular forces. Okay? So if you don't remember any other intermolecular forces, I'd be happy with that. We can stick with those three. Okay? We're going to talk about this last one here in a second, but I don't want to walk through it. Very similar to what we would see for the dipole-dipole. Intermolecular forces. So ionic or electrostatic. When did we see the ionic or electrostatic force? What kind of bonding did we have? We had ionic bonding. Okay, or I'm going to say ionic bonds. So we know we're looking at the intramolecular. Okay, dipole-dipole force. When did we get that? We had polar covalent bonds. And London dispersion or van der Waals, when did we get those? When we had nonpolar covalent bonds. So all that pressure and trying to get you guys to understand the different bond structures comes into handy because now that allows us to understand the different forces. Okay? So if we can look at an individual bond, we can then predict something about how it's going to interact with other molecules. Okay? You'll notice I've got a fourth one up there, hydrogen bonding. Okay? Probably an exceedingly important one, particularly if you move into biochemistry. Why is bonding in quotes? It's not a bond, it's intermolecular force. Okay? When do we have hydrogen bonding? Okay, water's got hydrogen bonding, yes. There's two cases, two rules that have to be satisfied for us to have hydrogen bonding. Okay, you're getting to the right idea. Rule number one, must have a dipole-dipole force. Okay, so two dipoles. What's rule number two? It's hydrogen bonding, right? What do you think we have to have in our structure? Maybe a hydrogen would be a good idea to include if we're going to have hydrogen bonding. Okay. We have to have a hydrogen bound. We're now looking at the physical bond to very particular elements. What particular elements does it have to be bound to?
Oxygen and
Fluorine, oxygen, and nitrogen. If we have a hydrogen bound to fluorine, oxygen, or nitrogen, we have hydrogen bonding as a possibility. Okay? Any one of those three we could immediately ignore, seeing as that this is an organic chemistry class. How many bonds can fluorine have? One. So if we satisfy our hydrogen bonding rule, we have to have the hydrogen bound to fluorine. There's our one bond. How many bonds are to a carbon? How many bonds could we put fluorine to as far as a carbon goes? But it's bound to hydrogen. How many carbons can I attach to that structure? None. Which element's going to be pretty irrelevant as far as organic chemistry goes? Fluorine. It can only bond to hydrogen. Great. We can now do hydrogen bonding. We won't see that in this class because there's no carbon. Okay? So let's hit some examples real quickly with our hydrogen bonding. I know I've got one up on the board, but I'm going to draw it again. So if you go back and reference the notes. So if we take a water molecule, and let's take a second one. Happy little tree, color it in blue here. And I'm going to take an orange. Let's do a little methane, just because methane's fun. I don't want to do it there. So I'm going to go back through in red now. Is this a hydrogen bond? No, what is that? It's a polar covalent bond that happens to be a bond between hydrogen and oxygen. That is not hydrogen bonding. How about the interaction here?
Oh, yes.
Yes.
Yes, that is hydrogen bonding. Okay? That was sloppy, but that says hydrogen bonding. We have a dipole from our oxygen hydrogen over here. We have a dipole from our oxygen hydrogen here. We have the dipole-dipole force. Do we have a hydrogen bound to oxygen or nitrogen? Yes. Hydrogen bonding is valid. How about over here?
Does the hydrogen in both molecules have to be bonded to nitrogen and oxygen, or just the hydrogen?
What we're looking at is that force. For that to be hydrogen bonding, what do we need? A dipole-dipole. Do we have a dipole from our water molecule?
Yeah.
Yes. Do we have a dipole between carbon and hydrogen?
No.
No, why not? It's a covalent bond. Do we have a dipole-dipole? No. Can we have hydrogen bonding? No. Does that make sense? So it's being careful with your classifications. We'll throw one more tricky one in here, just because it's fun. Go back to that oxygen, and let's say formaldehyde. Is that interaction hydrogen bonding? Erase all the others so you don't get confused. Do we have hydrogen bonding there? Is there a dipole between the oxygen and the hydrogen? So there's dipole 1. Is there a dipole between oxygen and carbon? What type of bond is that? That is a polar covalent bond. If we have a polar covalent bond, do we have a dipole? Yes. I now have a dipole-dipole force. Within that dipole-dipole, do I have a hydrogen bound to oxygen or nitrogen? Yes. What type of interaction do I have? Hydrogen bonding. Okay? Those questions can become exceedingly tricky. You'll see hydrogen bonding, like I said, a lot in biochemistry. Okay? Questions about hydrogen bonding or any of those other forces? Okay. So let's jump to kind of the summary slide of all of this. Okay. I like this chart, though it's a little bit difficult to interpret to begin with, which is why we're ending with it. This shows the relationship between our bonds and forces. You'll notice that what I'm trying to represent here is a color wheel. We're not looking at this is only covalent, this is only polar covalent. We get a gradation from covalent up to polar covalent. Somewhere in between would be a really polar covalent bond or a really non-polar polar covalent bond. Okay? It doesn't directly translate as one over the other. Okay? This can continue upwards. As we shift upwards, we see an increasing polarity. Why do we see increasing polarity? We're starting to form ions, positives and negatives. Okay? What happens when we make that transition over to our ionic force? Okay? How did we get that red ionic force? Where did that come from? That had to come from an ionic bond. What type of ionic bond? Well, a red one. Okay? If we take a look at a green polar covalent bond, what type of force is that going to generate? A green force that's somewhere between hydrogen bonding and dipole-dipole. Why do we not ever specifically say it's dipole-dipole? Sorry, that's hydrogen bonding that I'm pointing to. Why do we ever not specifically say it's hydrogen bonding? Because it has to be dipole-dipole first. If you've got a polar covalent bond, you're generating a dipole-dipole force. You can then evaluate further, can it be hydrogen bonding or not? Okay? So the idea is to use the color wheel to match correspondingly across it to determine what kinds of forces or bonds you've got. Why is that important? Well, these interactions, particularly your forces, are the things that determine all physical properties. Melting point, which you'll see in lab today. Boiling point. Solubility. Okay? Predicting all of those things comes back to these intermolecular forces. Okay? Predicting reactivity is ultimately going to come back to these intermolecular forces. Quiz. Question 8 is looking back to something along these lines. Looking for differences in electronegativity to try and predict something about the reactivity. Okay, so being able to interpret and manipulate this is going to be huge as far as doing well in this class. Okay, so let's attempt it really quickly here with a melting point. Okay, let's pick 2 compounds. What's your favorite compound? I lied, don't do that because you'll probably give me something harder. Let's pick water and apparently it's on the brain today. Methane. What type of intermolecular force does water have? Okay, so you answered the question I've been asking earlier today. What type of bonds does water have? Polar covalent. What type of force? We get hydrogen bonding, which is a dipole-dipole. Why do we classify hydrogen bonding as a separate class? It's more specific and it's usually stronger. Most hydrogen bonding interactions are a lot stronger than your dipole-dipole forces. Why? The difference in electronegativity is huge. You're picking the 3 most electronegative elements, and as far as organic is concerned, the least electronegative element. Okay? You're going to get a massive difference in electronegativity there. Okay? If we move to methane, what types of bonds do we have in methane? We're looking at just covalent. What does that mean for force? London dispersion force. Which is the stronger force? Hydrogen bonding or London dispersion? Hydrogen bonding. So if I'm going to look at trying to melt, say, ice versus methane, okay, it's going to require much more energy to remove a molecule of ice away from the structure as it will a molecule of methane, because water is holding on to its other water molecules to try and stabilize that charge. Methane could care less. There's no strong interaction, which means if I give it a little bit of heat, what happens? Instantly moves up into a higher phase. Okay? So you can apply the strength of your intermolecular forces into predicting melting points and boiling points. As far as physical properties go, your textbook will talk about every functional group based on their melting points and boiling points. It all comes back to this. You have now been taught it, which means we probably won't talk about it again for each functional group. Okay? Solubility is a lot trickier. We'll talk about that in lab. I won't test you directly on solubility in lecture because it's a bit tricky. Sorry. Questions before we move on to acids and bases? Okay. The only thing left on quiz 2 that we haven't talked about yet would be functional groups. I probably will not get to functional groups today, okay? Which means we can push that back to next Monday. I don't have any problems with that, okay? I will give quiz 3 next week, if not Wednesday, okay? Probably next week, just saying, okay? Is that clock right too? Yeah, it is. So when we move into acids and bases, pretty sure I put all the homework on the initial slide, so I took it off of here for some reason. Okay? Acid and base chemistry is the simplest chemistry that we could work with. Okay? Any guesses why that might be, or any hints as to why you may think that it's the simplest chemistry? Chemistry did you do in Gen Chem? Acids and bases. Okay, so acid-base chemistry is something that's fairly easy to do, very replicable. Okay, it's also very reversible. Okay, so it's an ideal chemistry because we can get things to go different directions and all over the different places. Okay, when it comes to organic chemistry, it's a lot trickier. We've got to play around with it a little bit more, and we end up seeing different types of reactions show up. Okay, so if we're going to look at our acid-base chemistry, it's helpful to have some idea of what our definitions might be. Okay, so you may have heard of these three definitions: your Arrhenius, your Bronsted-Lowry, and your Lewis acid. Which one came first? The Arrhenius. Which one's the most useless? The Arrhenius. So we're just going to skip that one. That definition, I can't even say it right. That's how often I don't teach that definition. It's so narrow that it just removes all applicability. Okay, so it's pretty much useless. So what we'll do is move into our Bronsted-Lowry definitions. Okay, so when we're looking at acids and bases, what are our definitions? Does anybody happen to remember the definitions of your acid and base?
Something that gives up or accepts a proton.
What's your favorite acid? LSD doesn't count. I'm just cutting it off before it happens. Hydrochloric. Thank you for picking a simple one. Hydrochloric acid. HCl. What happens when we add that into water? We get H plus and Cl minus. Why do we get H plus? Why not Cl plus? Why does chlorine take the electrons away from hydrogen? Chlorine is more electronegative. Okay? Still comes back to those electronegativities, being able to apply those. So if we take a look at HCl, which we've decided is now our favorite acid, which, by the way, will be your favorite acid for the rest of the semester. So when I ask again, that's what I'm asking for. H plus. So our favorite acid gave up H plus. It also gave up Cl minus, though. Maybe Cl minus is the part we're concerned about. Which is the dangerous species, H plus or Cl minus? Okay, have we seen Cl minus show up in some other species before? Maybe add it to your food every day. Sodium chloride. Add it to water, what do you get? Ooh, very, very similar. I take a solution of HCl, throw it in your face. I'm not going to do that. That's mean. Don't do that. Versus a solution of sodium chloride. Which one are you going to sue me over? HCl. Both of them supply the chloride ion. You didn't care about the sodium chloride, so what does that mean about which of these two is more reactive? Hydrogen ion. So our acid, as far as Bronsted-Lowry goes, because HCl happened to be his favorite acid too, or their favorite acid, our acids are going to be H plus donors. Okay, this gets simplified. Okay, we can try and make that even easier. How many electrons does a hydrogen atom have? Atom. 1 electron. How do I get H plus? I get rid of the electron. What's left? A proton. And just a proton. There's man. There are no neutrons in hydrogen. So all we're left with is a proton. So what are we going to start referring to when we look at our acids? We're looking at it as a proton donor. Okay? Acids and bases are opposites of each other. Okay, so what do you think a base is going to do? It's going to accept a proton. So we're looking at a proton acceptor. Whenever I say acids and bases in class, I'm typically referring to the Bronsted-Lowry definition. So we're looking at hydrogen ions being transferred back and forth. Okay? Let's think way back to what, 3 lectures ago, however many lectures ago it was that we talked about it. I said there was our atomic structure. We had protons, electrons, and neutrons. And of those, I said only one of those was really, really important to organic chemistry. Which one of those was that? The electrons. Electrons were so important that we were concerned about hybridization, where the electrons actually existed within the atom. Okay? So let's start being organic chemists and look back at our Bronsted-Lowry definition. How many electrons are in a proton? Don't get all quantum physics-y on me. None. This is a pretty crappy definition as far as organic chemistry goes. We care about how the electrons move. And yet, what's our definition say? Protons. Okay, so it has nothing to do with the electrons. Okay, so Lewis came along, the same Lewis that gave you Lewis structures, said those definitions aren't applicable enough for what we're doing in organic chemistry. We're concerned about the motion of electrons. We need to adjust our theory. Okay? So he had to come up with 2 new definitions for our acids and bases. These are the most broad definitions that you'll get and the most applicable. Okay, so let's see what we can do with them. We just said something important about them. We said that we want to look at the electrons. So we can start off with electrons. Because I don't want to write out electrons ever again like that. There's electrons, and that equals E minus, just so you know. Okay, so my definitions are going to be centered around electrons and how the electrons move. Okay, this one's a little bit trickier to try and nail down. But we've got our definitions of acids and bases, so we can play around with those to see if we can come up with a way to represent how the electrons move. Okay, so let's look at a nice simple acid-base reaction. Okay, we just talked about dissolving HCl in water. So what we're going to do now, though, is actually have it react with water, if we will, and see what happens. So we start with HCl. In a reaction, we put in a plus sign. You'll swiftly see I'll stop adding those. Plus H2O. Problem number 1 with what we've drawn. I don't see any electrons, so we should add all our electrons to this. What's our product? Theory, this might be pulling back from your memory from Gen Chem classes. You should remember what your products are. Kind of, sort of, maybe not at all. Really? We end up with H, also known as H3O plus, and Cl minus. Could we have predicted that from our understanding of differences in electronegativity? Or in particular, our understanding of what an acid is? What was the reactive part of HCl? Sorry, what was that? Try again. Not H. Not just hydrogen. I'm being picky, I know. H plus, a positive hydrogen. What do we need to stabilize a positive hydrogen? A negative. Okay? Well, chlorine already has a bunch of electrons. Are those stabilizing that positive hydrogen? If they were, would we have HCl as a strong acid? No. Okay? So the electrons on that chlorine are useless, which means what do I need to find? I'm going to have to find electrons somewhere else to stabilize that positive. Where do I have electrons? Somewhere else. Say on that oxygen, we've got 2 lone pairs. So what we can do is take those lone pairs and share them with the hydrogen. How many bonds would that hydrogen then if we start to share electrons? Bonds would that hydrogen have if we shared electrons? There's our hydrogen. We're going to have the oxygen's electrons share with the hydrogen. If we share electrons, what are we doing? We're forming a bond. So that arrow is showing the flow of electrons from oxygen to hydrogen. I've shared electrons, so that arrow represents the formation of a bond. There's one bond. How many bonds does hydrogen already have attached to it? 1. So how many bonds does hydrogen have? 2. How many bonds can hydrogen physically have? 1. We've got a problem. Hydrogen has too many bonds, so what should we do? To break the bond. We've got 2 options. We break the bond that we just formed, or break the other bond. So what we need to do is get the electrons away from that hydrogen. Hydrogen has too many electrons around it. Where are our electrons in that bond? That was dumb. How many electrons are in our bond? 2. So what we want to do is show those electrons moving away from the hydrogen. How can I do that? I'm going to show those electrons shifting towards the chlorine. I don't want to show them going off into space. I want to show them go to the atom. Why do they not go off into space? How stable is an electron? Not really stable at all. Which means if we showed those electrons going off into space, they're going to go crazy and destroy something. So we need to have something hold on to them, keep them a little bit stable. We're going to show those electrons moving to the chlorine. What's the result of this? H2O. Did I change the H2 of my oxygen? Nope. So when we draw out my product, there it is. And it's still bound to the oxygen. Okay? But we've added another hydrogen. So we can show that new bond in there. Hydrogen is now bound to water. What happened to our water molecule, though? One of those lone pairs turned into a bond. So, don't show that lone pair anymore. What happened to the other one? Nothing. So let's draw it. What happens to the charge? Lost electrons, so should become positive. What happened to the chlorine? Gained electrons, so it's negative. What we've just done there is a mechanism. Okay? We showed how the electrons moved through our structures or between our molecules to produce our products. Okay? Most of this semester, the second half of the semester, is going to be all about showing mechanisms and showing these curved arrows. Okay? We've already started to do it with resonance. We're now moving into reactions, starting to move those electrons around. Okay? So be aware of that. So back to our phrase, our initial intent. We're trying to show the flow of electrons. HCl was what? What kind of a species? What do acids react with? What do you think water acted as?
In this case, please.
Good call. Okay? So let's try and apply this. Where did our electrons start? It's the easiest place. Our water. So let's go ahead and look at our base. Water acted as our base. What did it do with its electrons? It gave them or donated them to hydrogen. So what is a Lewis base? An electron donor, or donating electrons. What happened to our acid? And this is where it gets a little bit dicey. Okay, it's the opposite of our base, so if we stick with that, we should be happy. Our acid, our Lewis acid, is an electron acceptor or accepting. I like the transformer name a little bit more. Okay? Make sense? Okay. That's the easy part. Those are just looking at our definitions of what each of these species are. Chapter 2 is primarily focused on our Bronsted-Lowry. Like I said, Lewis are going to become more relevant for us, but we'll come back to that when we start looking at our actual reactions beyond acids and bases. Okay? So what can we do with our Bronsted-Lowry definitions? Okay? One of the things that, at least in 151, you were required to memorize here at Mesa were your strong acids. I think you were required to memorize. Thought you were. Maybe not. Okay? So I would highly recommend that you memorize those again. Okay? So I'm going to condense it a little bit because I think they asked you to memorize 7. There's 6. I can only remember 6, so that's what we stuck with. Okay? We're looking at HI, HBr, HCl, H2SO4, HNO3, also known as hydroiodic, hydrobromic, hydrochloric, sulfuric acid, nitric acid. Okay? So those are nice, strong acids. That's cool, except you'll notice how many carbons are in those compounds. What class was this again? Organic chemistry. We need carbons. Where's most of our chemistry going to be concerned? And the not strong, looking at our weak acids. So more so than you will have seen probably in either 151 or 130, you need to be able to look at the acidity of individual atoms and try and predict their reactivity. Are they more acidic or less acidic than another thing? Okay? When it comes to our strong acids, we always say those are super strong. Our weak acids, I will never ask you what is the acidity of acetic acid. I'll ask what's the acidity of acetic acid in comparison to water. Any guesses? It's probably more acidic. Why? What was the name? Acetic acid. Probably more acidic than water. Okay, we even put it in the name. Okay? So being able to rank our acid strengths becomes really important. This is going to come back to a lot of our explanations on how we'll go through and rank things. Okay, we've already talked about stability. When we're looking at stability of our acids and bases, we're always trying to minimize the energy or charge with an individual system. Okay? So everything is striving to minimize as best as possible. Okay? So when we're looking at acids and bases, particularly in comparison or comparing things, we're going to look at where the charge is going to be most stable. Okay, so what charge do you think we're going to look for when we're going to compare acids and bases? Or sorry, acids. What charge should we be concerned about? Give me an example acid. Favorite acid? Hydrochloric acid. Changed my mind. I like HA better. What does A stand for? Any acid. Okay? If I'm going to look at acid base or acid strength, I want to be concerned about the charge that starts to build on my atom. So if I'm going to compare HA to something else, I want to see which atom can hold the charge better. Okay, if we're going to rank Bronsted-Lowry acids, which charge is always going to be the same? Say I compare HA to HB. Hydrogen always going to be positively charged. Is that ever going to change? Can I ever change the stability of that hydrogen ion? No. So when we're talking about which one is more stable, where our charge is, we're looking for the negative charge. Okay, so ultimately we're referring to the conjugate base. If we get rid of that hydrogen, it's going to leave a charge. And what charge would it leave? A negative charge on our other species. And if we now try and compare A and B, I want to place the charge, or our stronger acid is going to be the one that can stabilize that negative charge better. Okay? How can we have something hold on to or stabilize negative charge? We've already talked about this answer already. It's not number 1, or 3, or 4. Electronegativity. The more electronegative an element is, tighter it's going to hold the electrons. the more it's going to take the electrons away from hydrogen. Well, if it takes the electrons away from hydrogen, what does hydrogen have? No electrons. What charge would it be? Positive. There's our acid. Okay? So one of the things we can use to compare things is looking at the electronegativity of the atom from which the hydrogen is coming. Okay? The stronger acids will be further to the right. What does further to the right mean? They're more electronegative. Okay? That's actually what it was supposed to say. I just forgot to save it apparently. Okay? You'll notice I've got that set as rule number 2. Rule number 1. Okay? We're going to look at the size of atom A and atom B. Okay? This one's a little bit trickier to think about. Down a column, our stronger acids are larger. So what happens as we move down a column? What happens to the atomic size? Gets bigger. Okay? So why would that matter? Okay? So let's take a look at, say, HF versus HI. Which one's the stronger acid? Which is a strong acid? HI. Which one's the stronger acid? HI. Okay? Even though its electronegativity is lower than fluorine. So we'll come back to that. So why is that the case? What we're looking at is, again, the ability of those atoms to hold the negative charge. F minus versus I minus. Which one can stabilize the negative charge better? If you look at electronegativity, fluorine's wicked electronegative. It should hold on to that charge really, really well. But somehow iodine is stabilizing it better. That's really weird. Okay, so let's look at the size effect. What's the difference in size there? How big is fluorine? Or rather fluoride? Really, really, really small. So there's our little fluorine atom. Okay, I need to draw it a little bit bigger than that. Okay, and if it's F minus, it has an electron. So our electron, let's go ahead and draw that in there. There's our electron. Okay, somewhere in that fluoride ion. Let's take a look at I minus. How big is I minus? Wicked huge. Yes, that is scientific. And there's iodine. How big is its extra electron? Exact same size as the fluoride. It's still an electron. Okay. What did we say about electrons? Stable, unstable? Unstable. Okay, so we want to make the electrons as happy as possible. What we're going to do is try a different situation here. Electrons are unstable. That's why you stick your finger in the electrical outlet. It hurts. Okay, we don't like doing that. Okay, think of that electron as an electrical outlet. Okay, I'm now forcing you. You have to stick your hand into one of those atoms. Iodide or fluoride? Why are you going to stick it in the iodide? You are less likely to hit that negative charge. Less likely to get that shock. What does that mean? You have effectively stabilized that electron by spreading it over a larger area. What are we saying? Size. The bigger the atom, the more stable that ion. Okay? Does that make sense? Okay. There are two other rules there. Briefly talk about those. I don't think I'm going to test you too much on those, but we'll discuss them. Rule number 3, it's referred to as induction. Okay? What's happening there is we're going to put our acidic hydrogen close to an electronegative element. Not directly bound to one, but close to it. Okay? So let's say we pick, that's an eraser. This compound versus, hey, guess what? Here's methane again. Which compound has the more acidic hydrogen? Top or bottom? The more acidic hydrogen. So we're looking at which atom So we remove that hydrogen, we put a negative charge on carbon. Does carbon like a negative charge? No, why not? 2 reasons. Less electronegative, low electronegativity, and how big is it? It's not very big at all, so it can't stabilize that charge. So that's not going to be very acidic to begin with. Okay, but let's set that aside. If we remove this hydrogen, we're still putting that negative charge on a carbon atom. So thinking about size, not a bad idea to try and shift out to the fluoride. Is the negative charge on fluoride or on carbon? It's on carbon. Size only affects where the charge is located. Carbon to carbon, no difference in size. How about electronegativity? No difference in electronegativity. Induction. What's the difference between these two? This one has a fluorine. What does this fluorine do to those electrons? Takes them away from carbon. What happens to carbon? It becomes more positive. It lost those electrons. Does carbon want to lose electrons? No, so what does it start to do? Takes them from the next available source. Where's the next available source? From the hydrogens. By putting that electronegative fluorine on there, we effectively increase the electronegativity of this carbon over this one. That is our inductive effect. Okay? So the presence of an electronegative atom will increase the acidity of our hydrogens because that electronegative atom starts to draw electron density away. Okay? Kind of neat. The last one is resonance. Okay? We won't look at resonance necessarily based on acid strengths, but it will come important as far as stability, so it's important to address here. If I take a look at this compound versus this compound. This is what we'll end with, and we'll come back to these examples Wednesday. Our top structure, where's our most acidic hydrogen? Do we have more than one hydrogen? Yes. This hydrogen's bound to carbon. Where's our other hydrogen? Oxygen. Which one's more acidic, oxygen or hydrogen, or carbon? Why the oxygen? More electronegative than carbon. Okay? Why do we not look at size? Because across a row, size is effectively the same. We talked about that, I think, last week. Okay? So we're looking at that last hydrogen as being our acidic one. When we go down and look at our second example, where's our acidic hydrogen there? The one on the oxygen again. If we go ahead and remove that, what charge builds on each of those oxygens? Less than positive. And not neutral. We get a negative charge. This is what I'll leave you to play around with. We'll talk about it tomorrow. This top one is our stronger acid. Ignore induction in this case. I don't want you to think about it in that way. Look for resonance. Come up with an explanation for why that top structure, due to resonance, is more stable than the bottom structure. Okay? Like I said, we'll start there on Wednesday and move from there. Didn't get into functional groups.